The Big Picture, on the Origins of Life, Meaning, and the Universe Itself. Introduction. Exploring life's big questions through science. Why are we here? What happens when we die? What is the meaning of life? These profound questions have intrigued humanity for centuries. Throughout history, we have sought answers through religion, philosophy, and mythology, only to encounter more questions than solutions. Sean Carroll's The Big Picture, on the Origins of Life, Meaning, and the Universe Itself, invites us to explore these existential mysteries from a scientific perspective, offering insights that transcend traditional boundaries. Carroll argues that science provides not just facts about the universe but also a framework for understanding our place within it. By integrating discoveries from physics, biology, and philosophy, he proposes a naturalistic worldview, a perspective that seeks meaning within the universe's intricate patterns without relying on supernatural explanations. This worldview, which he calls poetic naturalism, balances the scientific rigor of understanding how the universe works with the emotional richness of human experience. The power of poetic naturalism. Carroll introduces poetic naturalism as a way to unify disparate elements of existence under a single, coherent framework. At its core, poetic naturalism acknowledges that there is only one reality, the natural world, but it allows for multiple ways to describe and interpret it. For example, the same reality can be described scientifically in terms of atoms and molecules or emotionally in terms of love, purpose, and joy. Each description is valid in its own context, providing complementary perspectives on the same truth. This approach bridges the gap between reductionist views that focus solely on fundamental particles and emergent perspectives that explore the complexities of human experience. By embracing poetic naturalism, Carroll encourages us to find meaning not in cosmic purpose but in the intricate patterns and connections of the universe we inhabit. A journey through the cosmos. The Big Picture takes readers on a sweeping journey through the principles that govern our universe, from the core theory of physics to the evolution of consciousness. Carroll delves into foundational concepts such as entropy, causation, and emergence, exploring how they shape our understanding of time, existence, and meaning. Along the way, he addresses age-old questions about the origins of life, the nature of free will, and the mysteries of the human mind, challenging us to think critically about the assumptions we hold. Science as a guide to meaning. One of Carroll's central arguments is that science, far from stripping life of meaning, enriches our understanding of it. By revealing the underlying mechanisms of the universe, science empowers us to appreciate its beauty and complexity. Carroll believes that even without a divine plan or predetermined purpose, we can create our own meaning by embracing curiosity, cultivating relationships, and contributing to the well-being of others. A call to wonder. As we embark on this exploration of the big picture, Carroll invites us to approach life's mysteries with both wonder and skepticism. He reminds us that while we may not have all the answers, the pursuit of knowledge is itself a source of fulfillment. The universe is vast, intricate, and often perplexing, but it is also an incredible gift, a canvas for our imagination and inquiry. Through the chapters that follow, we will delve into the principles that shape our reality, uncover the origins of life and consciousness, and discover how science offers a framework for navigating life's biggest questions. Together, let us embark on this journey of exploration, where science, philosophy, and human experience converge to illuminate the big picture of existence. Chapter 1. The Foundation of Physics. What is the universe made of, and how does it work? Sean Carroll begins his exploration of life's big questions by delving into the foundation of modern physics. At its core, physics seeks to explain the fundamental rules that govern the cosmos, from the tiniest particles to the largest galaxies. In this chapter, Carroll introduces the core theory, a framework that unites our understanding of particles, forces, and their interactions. The search for explanations. Before modern science, humans relied on myths, religion, and supernatural beliefs to explain the mysteries of existence. Thunderstorms, earthquakes, and illnesses were seen as acts of gods or spirits. These explanations, while comforting, often stem from fear and lack the rigor of evidence. With the advent of the scientific method, humanity began unraveling the complexities of the natural world, replacing myths with testable theories. One of the most profound achievements of science is the core theory. This framework encompasses the standard model of particle physics, which describes the fundamental particles, like quarks and electrons, and the forces, like electromagnetism and nuclear forces, that govern their behavior. Together with Einstein's theory of general relativity, the core theory provides a near-complete picture of how the universe operates at both micro and macro scales. The core theory and everyday life. While the core theory might seem abstract, its implications are deeply relevant to our daily existence. It explains the behavior of matter, the interactions that hold atoms together, and the forces that govern motion. From the glow of a light bulb to the signals in our brain, the core theory underpins every aspect of our physical reality. Carroll highlights how the core theory even addresses phenomena often considered supernatural. For example, telekinesis and telepathy, popular in science fiction, would require particles or forces that are absent from the natural world. According to the core theory, if such phenomena were real, they would have been detected and replicated in experiments. The absence of evidence confirms that these abilities, while imaginative, are not physically possible. Symmetry and the elegance of nature. A key feature of the core theory is symmetry, a principle that describes how certain properties of the universe remain unchanged under specific transformations. Symmetry lies at the heart of many natural phenomena, from the conservation of momentum to the invariance of physical laws over time. It helps physicists identify patterns and formulate laws that are consistent and universal. For example, the crossing symmetry within the core theory explains why certain particles cannot exist under the conditions necessary for telekinesis. The absence of these particles reinforces the predictive power of the core theory, demonstrating its reliability in explaining natural phenomena. The limits of the core theory. Despite its successes, the core theory is not without limitations. It does not fully integrate gravity with quantum mechanics, leaving questions about the nature of space-time and black holes unanswered. It also cannot address subjective experiences like consciousness or the meaning of life. Carroll acknowledges these gaps, not as failures, but as opportunities for future exploration. The role of physics in understanding reality. Carroll emphasizes that the core theory is more than a collection of equations. It is a testament to humanity's ability to comprehend the cosmos. By understanding the rules of physics, we gain a deeper appreciation for the complexity and beauty of the universe. This knowledge not only empowers technological progress but also fosters a sense of wonder about our place in the grand scheme of existence. A foundation for the big picture. As the chapter concludes, Carroll invites readers to view the core theory as a foundation for exploring life's biggest questions. While it cannot tell us why the universe exists or what gives life meaning, it provides a reliable framework for understanding how the universe operates. This understanding, in turn, equips us to think critically about the mysteries that remain. The next chapter challenges one of the most long-standing principles of human thought, the law of cause and effect. Through the lens of modern physics, it will reveal how this principle, once considered fundamental, may be more complex than we ever imagined. Chapter 2. The Law of Cause and Effect. Is everything we observe in the universe the result of cause and effect? For centuries, this principle has been a cornerstone of human understanding. From ancient philosophy to modern science, causation has been seen as the mechanism by which events unfold. However, Sean Carroll invites us to reconsider this assumption. Through the lens of modern physics, he explores how cause and effect, while intuitive, may not be as fundamental to the universe as we once believed. The intuitive appeal of cause and effect. In our everyday lives, cause and effect seem inescapable. A rock thrown into a pond creates ripples. Pressing a key on a piano produces sound. Our understanding of the world is built upon this framework. Actions lead to outcomes. This principle has been a guiding force in disciplines from engineering to medicine, allowing us to predict and manipulate events with remarkable success. Historically, philosophers like Aristotle and Hume pondered causation's role in shaping reality. Even Newton's laws of motion, foundational to classical physics, align with the notion that every action has an equal and opposite reaction. But as science advanced into the realms of quantum mechanics and relativity, cracks began to appear in this seemingly immutable law. The challenge of momentum conservation. To challenge the idea of universal causation, Carroll introduces a thought experiment. Imagine an object floating in the vacuum of space. There are no forces acting upon it, no external influences to set it in motion. Yet, according to the principle of momentum conservation, the object will continue moving indefinitely in a straight line. This movement occurs not because something caused it, but because motion itself is a natural state when unimpeded. Momentum conservation, a cornerstone of physics, demonstrates that some phenomena exist independently of cause and effect relationships. This realization forces us to reconsider causation's role in governing the universe. Quantum mechanics and the nature of time. The advent of quantum mechanics introduced even greater challenges to the traditional view of causation. In the quantum realm, Particles do not behave in deterministic ways. Instead, their behavior is governed by probabilities. For example, the position of an electron around an atom cannot be predicted with certainty, only estimated as a probability cloud. Quantum entanglement adds another layer of complexity. When two particles become entangled, measuring the state of one particle instantly determines the state of the other, regardless of the distance between them. This phenomenon defies classical notions of causation, suggesting that events can be correlated without a direct causal link. Time and the arrow of causality. Our perception of causation is deeply tied to our understanding of time. We think of causes as preceding effects. A cue ball strikes another ball, setting it in motion. But time itself may be more fluid than we realize. Carroll explores the concept of time as an emergent property rather than a fundamental dimension. Entropy, the measure of disorder in a system, gives rise to the arrow of time, which moves from low entropy, order, to high entropy, disorder. This progression creates the illusion of causality by defining a direction in which events unfold. Without entropy, the distinction between cause and effect could blur entirely. The limits of causation. Carroll emphasizes that while causation is a useful tool for understanding the macroscopic world, it is not a universal law. At the fundamental level of particles and forces, causation often gives way to deeper principles like conservation laws and quantum probabilities. This does not invalidate cause and effect, but situates it as an emergent phenomenon, one that arises from the complex interactions of simpler, more fundamental rules. Implications for our understanding of reality. The re-examination of causation has profound implications for how we view the universe and our place within it. If causation is not a fundamental law, it challenges deterministic views of reality, including the belief that all events are inevitable consequences of prior actions. It also invites new questions. How do emergent phenomena like consciousness and free will fit into a universe where causation is not absolute? A new perspective. Carroll invites us to embrace a more nuanced understanding of cause and effect. Rather than seeing it as a universal principle, we can view it as a useful approximation, one that applies to the scale of human experience but may not hold at the deepest levels of reality. Chapter 3. Fundamental and Emergent Theories. How do we make sense of the universe's complexity? Sean Carroll introduces two complementary ways of understanding reality, the fundamental and the emergent. These perspectives allow us to explore the universe on vastly different scales, from the minute interactions of particles to the grand phenomena of clouds, ecosystems, and consciousness. This chapter demonstrates how these theories intertwine to reveal a richer understanding of the world. The fundamental viewpoint, reality at its core. The fundamental perspective seeks to uncover the universe's building blocks. It focuses on the simplest, most basic components of reality, particles, forces, and the mathematical rules that govern their behavior. This viewpoint is the domain of quantum mechanics, the Standard Model, and the core theory, which describe how the smallest units of matter interact to form the universe we observe. From this vantage point, the universe is a collection of particles and forces in motion. Clouds, for example, are not inherently clouds in this view. They are aggregations of water molecules, influenced by gravity, temperature, and atmospheric pressure. Understanding the behavior of individual molecules enables us to predict the behavior of the whole. The emergent viewpoint, seeing the bigger picture. The emergent perspective, in contrast, zooms out to focus on complex systems and their higher-order behaviors. While the fundamental view explains what clouds are at the molecular level, the emergent view examines how clouds function within the broader context of weather systems, climate, and their effects on life on Earth. It looks at how parts combine to form a whole and how new properties arise that are not evident at the fundamental level. Emergence occurs when simple components interact to create complex behaviors that cannot be fully understood by examining the parts in isolation. For example, individual neurons in the brain have simple functions, but their combined activity gives rise to consciousness, a phenomenon that cannot be fully explained by studying a single neuron. The relationship between fundamental and emergent theories. Carroll emphasizes that these perspectives are not in competition. Rather, they are complementary tools for understanding the universe. The fundamental viewpoint provides the raw ingredients, while the emergent perspective reveals the recipes and patterns that arise from their interactions. Take the example of water. At a fundamental level, water is a collection of H2O molecules interacting via hydrogen bonds. However, the emergent properties of water, its ability to freeze, boil, or flow, are best understood at a macroscopic level. The fundamental rules do not disappear, They are the foundation for the emergent properties, but they cannot fully describe the larger phenomena. Why emergence matters. Emergent theories are crucial for tackling the complex challenges of science and life. Carroll highlights how emergence allows us to address phenomena that are too intricate to study purely at the fundamental level. These include 1. Biology. Understanding ecosystems requires examining relationships between organisms, rather than focusing solely on their molecular composition. 2. Weather systems. Predicting storms involves modeling large-scale atmospheric dynamics, not just the motion of individual air molecules. 3. Consciousness. The study of the mind requires exploring networks of neurons and their collective behaviors, rather than reducing thought to atomic interactions. Emergence also helps us bridge the gap between science and human experience. While fundamental theories explain the mechanics of existence, emergent theories capture the richness and complexity of life as we perceive it. The challenges of integration. While fundamental and emergent theories are both valuable, integrating them presents challenges. For one, emergent phenomena often involve an overwhelming number of interacting parts, making them difficult to model or predict precisely. Additionally, emergent systems can exhibit behaviors that seem unpredictable or chaotic, even though they ultimately adhere to fundamental laws. Carroll acknowledges that these difficulties do not undermine the validity of either perspective. Instead, they highlight the need for flexibility in choosing the right framework for a given problem. A universe of layers. Carroll suggests that the universe can be thought of as a series of layers, each with its own rules and patterns. Fundamental theories govern the bottom layer, the domain of particles and forces, while emergent theories describe the layers above, from chemistry to biology to sociology. Understanding the interplay between these layers enriches our comprehension of the universe and our place within it. The big picture in science and life. As the chapter concludes, Carroll reflects on how fundamental and emergent theories contribute to the big picture. While the fundamental view provides a foundation of truth, the emergent view adds context and meaning, helping us navigate the complexities of existence. Together, they form a holistic approach to understanding reality. Chapter 4. The Power of Entropy. What governs the flow of time and the emergence of complexity in the universe? Sean Carroll introduces entropy, a concept rooted in thermodynamics, as a key to understanding the arrow of time, the rise of order and disorder, and the evolution of the cosmos. This chapter explores entropy's profound implications for the structure of reality and the human experience of time. What is entropy? At its core, entropy is a measure of uncertainty, randomness, or disorder within a system. It reflects how energy is distributed and how much of it is unavailable for useful work. Carroll describes entropy as a kind of cosmic bookkeeping that tracks the transformation of energy from organized, usable forms to dispersed, unusable states. For example, consider a melting ice cube in a warm room. Initially, the ice cube represents low entropy. Its water molecules are tightly organized in a crystalline structure. As it melts, heat energy flows into the ice, breaking the structure apart and increasing the disorder of the system. This natural progression from order to disorder demonstrates one of entropy's key principles. It always increases over time in a closed system. Entropy and the arrow of time. Entropy provides a scientific basis for one of our most intuitive experiences, the passage of time. We perceive time as flowing in one direction, past to future, because entropy increases in that direction. This is often called the arrow of time. Imagine a broken cup. While it is easy to picture a whole cup falling and shattering into pieces, the reverse process, broken pieces spontaneously reassembling into a cup, is practically impossible. This irreversibility arises because the shattered state has higher entropy than the organized state, making it statistically unlikely for entropy to decrease. Carroll emphasizes that this increase in entropy is not just a property of physical systems but a fundamental feature of the universe. It explains why we remember the past but not the future, why causes precede effects, and why life unfolds in a sequence of events. Without entropy, the arrow of time would vanish, and the universe would be a static, timeless expanse. Entropy and complexity. While entropy is often associated with disorder, Carroll highlights a paradox. Increasing entropy can give rise to complexity and structure. This counterintuitive process occurs because entropy does not increase uniformly. It creates pockets of order amidst overall disorder. For example, stars, planets, and galaxies form as matter clumps together under gravity, creating highly organized systems. Similarly, life on Earth emerged from the interplay of energy flows and chemical processes, resulting in intricate organisms and ecosystems. These phenomena show that the universe's march toward disorder also fosters creativity and innovation, enabling complexity to flourish. The role of entropy in human experience. Entropy shapes not only the physical world but also our perception of reality. It governs the asymmetry of time that defines our lives. We age, we remember the past, and we plan for the future. Our understanding of entropy also deepens our appreciation for the fragility and transience of existence. Carroll reflects on how entropy's relentless increase highlights the impermanence of all things. Stars will burn out, galaxies will drift apart, and the universe will approach a state of maximum entropy, a vast expanse of equilibrium known as heat death. While this may seem bleak, Carroll encourages us to find meaning in the fleeting moments of order and complexity that arise along the way. Entropy in science and society. Beyond its implications for physics, entropy has inspired insights in fields as diverse as information theory, biology, and economics. For instance, 1. Information theory. Entropy measures the uncertainty or randomness in a dataset, forming the basis of modern computing and communication technologies. 2. Evolution. Entropy drives the flow of energy through ecosystems, enabling life to adapt and evolve in response to changing environments. 3. Economics. Entropy models have been used to study market dynamics, resource distribution, and the flow of innovation. These applications demonstrate entropy's versatility as a tool for understanding complex systems across disciplines. A universe in motion. Carroll concludes by emphasizing that entropy is not just a measure of disorder, but a lens through which we can view the universe's evolution. From the Big Bang to the present day, the cosmos has transitioned from a state of low entropy and simplicity to one of high entropy and rich complexity. This dynamic process, driven by the interplay of energy and matter, underpins the very fabric of existence. In the next chapter, he will examine how entropy and evolution intersect, revealing how randomness and uncertainty give rise to order, innovation, and the complexity of living systems. This interplay offers profound insights into the origins of life and the forces that drive its continued development. Chapter 5. Entropy and Evolution. How can randomness and disorder give rise to the complexity and order of life? In this chapter, Sean Carroll explores the interplay between entropy and evolution, revealing how the apparent chaos of increasing entropy fosters the emergence of organized systems. By connecting thermodynamics with biology, Carroll demonstrates how the universe's march toward disorder paradoxically enables the intricate complexity of life. The surprising role of entropy in life's complexity. At first glance, entropy seems antithetical to life. Living organisms are highly ordered systems, from the precise folding of proteins to the intricate workings of cellular processes. How can such order coexist with the universal tendency toward increasing entropy? Carroll explains that life does not defy entropy but operates within its framework by creating local pockets of order at the expense of increasing disorder in the environment. For example, plants absorb sunlight and convert it into chemical energy through photosynthesis, creating ordered structures like glucose molecules. However, this process also releases heat and increases entropy in the surrounding environment. This principle, local order at the cost of global disorder, is fundamental to all living systems. The emergence of complexity. Carroll highlights how entropy drives the formation of complexity in two key ways. 1. Energy flow. Life thrives on the flow of energy through systems. The Earth, for instance, is bathed in energy from the sun, which powers the processes that sustain life. By consuming and dissipating this energy, organisms build and maintain complex structures. 2. Nonlinear dynamics. Entropy does not increase uniformly but follows patterns that allow for the emergence of complexity. For instance, self-organizing systems, such as hurricanes or cellular automata, arise from simple rules and interactions, demonstrating how intricate patterns can emerge from seemingly chaotic conditions. These principles apply not only to living organisms, but also to ecosystems and planetary systems, illustrating the universality of entropy-driven complexity. Entropy and evolution. Carroll connects entropy to evolution, explaining how natural selection leverages randomness to drive adaptation and innovation. Evolution operates through variation, selection, and inheritance. Random mutations introduce diversity, and advantageous traits are preserved and passed on to future generations. Entropy plays a crucial role in this process by generating the randomness needed for variation. Without entropy-driven molecular interactions, the genetic mutations that fuel evolution would not occur. This interplay between randomness and selection enables life to adapt to its environment and develop greater complexity over time. The cosmic evolution of life. Carroll expands the discussion to consider life's evolution on a cosmic scale. The universe began in a state of low entropy following the Big Bang, with energy concentrated in a hot, dense plasma. As the universe expanded, entropy increased, allowing matter to clump together under gravity to form stars, galaxies, and planets. On Earth, these conditions created a unique environment for life to emerge. The planet's energy flow, driven by sunlight, enabled the formation of complex molecules and the eventual development of living systems. Over billions of years, evolution produced the astonishing diversity and complexity of life we see today. Entropy's dual nature, chaos and creativity. Carroll emphasizes that entropy is not merely a force of disorder but a source of creativity and opportunity. The same processes that increase entropy also create the conditions for complexity to flourish. This dual nature of entropy highlights the universe's dynamic balance between order and chaos, providing a foundation for understanding life's emergence and evolution. Implications for humanity. Entropy's role in evolution has profound implications for how we view humanity's place in the cosmos. Carroll argues that understanding entropy helps us appreciate the delicate interplay of forces that sustain life. It also underscores the importance of preserving the fragile balance of Earth's ecosystems, which depend on the flow of energy and the maintenance of order. Moreover, entropy reminds us of the impermanence of life and the universe itself. While this perspective may seem sobering, Carroll encourages us to find meaning in the fleeting beauty of complexity and to celebrate the extraordinary conditions that make life possible. A framework for understanding life. Carroll concludes the chapter by framing entropy and evolution as complementary forces that shape the universe. Entropy drives the flow of energy and the emergence of complexity, while evolution channels randomness into organized systems capable of adapting and thriving. Together, they offer a powerful framework for understanding life's origins and its continued development. Looking to the mind. As this chapter closes, Carroll sets the stage for the next frontier of exploration: the evolution of consciousness. How did the human mind arise from the interplay of entropy and evolution? In the following chapter, he will dive into the origins of consciousness, examining how physical processes gave rise to awareness, thought, and the unique qualities of human experience. Chapter 6: The Evolution of the Mind. How did the human mind, a realm of thoughts, emotions, and self-awareness, emerge from the physical processes of the universe? In this chapter, Sean Carroll delves into the origins and evolution of consciousness. Building on the principles of entropy and evolution, he examines how the complex and enigmatic phenomenon of the mind arose from the interplay of biology, physics, and adaptation. The nature of consciousness. Consciousness is one of the most profound mysteries of existence. It encompasses our ability to perceive the world, experience emotions, and reflect on our thoughts. Despite its central role in human life, consciousness has long defied precise definition or explanation. Carroll approaches it as an emergent phenomenon, arising not from any single particle or mechanism but from the intricate interactions of neurons within the brain. At its core, consciousness is rooted in the physical processes of the brain. Neurons transmit electrical signals, forming networks that process information. These networks generate patterns of activity, which correspond to sensations, memories, and decisions. While this explanation captures the mechanics of thought, it raises deeper questions. How do physical interactions give rise to subjective experience? What makes a collection of atoms capable of self-awareness? The evolutionary origins of the mind. To understand consciousness, Carroll traces its evolutionary roots. He highlights the work of scientists like Malcolm McIver, who theorized that the transition from aquatic to terrestrial environments played a critical role in the development of cognition. Aquatic organisms, limited by their underwater vision, primarily react to immediate stimuli. But the transition to land allowed early vertebrates to see farther and detect threats from a distance. This shift enabled planning and decision-making, laying the groundwork for more complex cognitive abilities. Over time, natural selection favored traits that enhance survival, such as memory, problem-solving, and social cooperation. These incremental changes culminated in the advanced consciousness seen in humans. The brain as an emergent system. Carroll emphasizes that consciousness is an emergent property, arising from the interactions of simpler components. Just as clouds form from water droplets and ecosystems emerge from individual organisms, the mind arises from the collective activity of neurons. This perspective highlights the brain's remarkable capacity to generate experiences far greater than the sum of its parts. Emergent phenomena in the brain are made possible by its complexity. With approximately 86 billion neurons and trillions of connections, the human brain is one of the most intricate systems in the known universe. This complexity allows for the integration of sensory inputs, the formation of abstract ideas, and the development of self-awareness. Consciousness and physical laws. Carroll situates consciousness within the framework of physical laws, arguing that it does not violate or transcend the core theory. Instead, consciousness operates within the constraints of physics, governed by the interactions of atoms, molecules, and forces. This naturalistic view suggests that while consciousness is deeply mysterious, it is not beyond the reach of scientific inquiry. However, Carroll acknowledges the challenges of understanding subjective experience. The hard problem of consciousness, how physical processes create the feeling of being, remains an open question. While science has made strides in mapping the brain and understanding its functions, the essence of subjective experience continues to elude precise explanation. The mind and the universe. Carroll reflects on the significance of consciousness in the context of the universe. As far as we know, the human mind is unique in its ability to contemplate the cosmos and its place within it. This capacity for self-reflection gives us a special role in shaping the future of life and understanding the universe's mysteries. Consciousness also provides a bridge between the fundamental and emergent perspectives explored earlier in the book. It links the physical laws that govern the brain's components with the subjective experiences that define our humanity. This duality underscores the richness of reality and the importance of integrating multiple viewpoints to understand it fully. Implications for meaning and purpose. The emergence of consciousness raises profound questions about meaning and purpose. If the mind is a product of physical processes, what does this imply for free will, morality, and the search for meaning? Carroll argues that consciousness does not diminish the significance of these concepts, rather, it enriches them. By recognizing that meaning arises from human experiences and interactions, we can create purpose in a universe that does not impose it. A continuing mystery. While much progress has been made in understanding the mind, Carroll acknowledges that consciousness remains a frontier of scientific exploration. Future discoveries in neuroscience, physics, and artificial intelligence may shed light on its origins and mechanisms, offering new insights into one of life's greatest enigmas. Looking forward, Carroll reflects on how the evolution of the mind fits into the larger story of the universe. Consciousness is not an anomaly but a natural outcome of the universe's drive toward complexity and adaptation. It represents the pinnacle of emergent phenomena, showcasing the profound potential of physical systems to create order, creativity, and self-awareness. Conclusion. Seeing the big picture. What does it mean to truly understand the universe and our place within it? Sean Carroll concludes the big picture by weaving together the complexities of science, philosophy, and human experience into a unifying vision. He calls this perspective poetic naturalism, an approach that embraces the rigor of scientific inquiry while honoring the richness and complexity of human life. A universe without supernatural meaning. One of Carroll's central arguments is that the universe operates according to natural laws, without the need for supernatural explanations or predetermined purpose. This naturalistic worldview challenges traditional notions of divine intervention or cosmic destiny, but it also empowers us to find meaning in our own lives. Without a preordained purpose, meaning becomes something we create through our relationships, actions, and aspirations. Carroll emphasizes that this perspective does not diminish the significance of life but enhances it by placing responsibility for meaning squarely in our hands. We are the authors of our own stories, capable of shaping a future that reflects our values and dreams. The beauty of poetic naturalism. Poetic naturalism, Carroll explains, is not just a way of understanding the universe but a way of living within it. It acknowledges the scientific truth that there is one reality, the natural world, while recognizing that there are many ways to describe and interpret that reality. For example, the same glass of water can be described in terms of its molecular composition, its role in quenching thirst, or its symbolic significance in a religious ritual. Each description is valid within its own context, reflecting the richness of human experience. Poetic naturalism encourages us to embrace this multiplicity, valuing both the objective insights of science and the subjective meanings we attach to the world. The Big Questions Revisited. Throughout the book, Carroll has tackled some of life's most profound questions. Why are we here? The universe exists as a natural consequence of physical laws, without requiring a deeper why. This realization frees us to focus on the how of creating meaningful lives. What is the meaning of life? Meaning is not an external property but an emergent one, arising from our choices, connections, and experiences. It is something we craft, not something we discover. What happens when we die? Consciousness is a product of the physical brain, and when the brain ceases to function, so does our experience. While this may seem stark, Carroll argues that it underscores the preciousness of the time we have. Science as a guide to meaning. Carroll reflects on the power of science not just to explain the universe, but to inspire awe and wonder. By uncovering the mechanisms of the cosmos, science reveals a world of staggering complexity, beauty, and interconnectedness. It shows us that we are not separate from the universe but an integral part of its ongoing story. This perspective invites us to live with curiosity, humility, and gratitude. It reminds us that even in a vast and indifferent cosmos, we have the capacity to create beauty, solve problems, and care for one another. Science, Carroll argues, is not a threat to meaning but a source of it, a tool for understanding the world and our place within it. Our place in the cosmos. Carroll concludes by situating humanity within the grand sweep of cosmic history. We are products of the universe's natural evolution, shaped by the interplay of entropy, energy, and time. Yet, as conscious beings, we possess a unique ability to reflect on this process and influence its direction. This duality, being both a part of the universe and an observer of it, gives us a profound responsibility. Carroll urges us to use our knowledge and creativity to address the challenges facing humanity, from environmental sustainability to social justice. By acting with intention and compassion, we can contribute to a legacy that transcends individual lifetimes. A call to wonder. As the book closes, Carroll leaves readers with a simple but powerful invitation to embrace the wonder of existence. The universe is vast and mysterious, filled with both questions and answers. While we may never fully understand it, the pursuit of knowledge and the creation of meaning are themselves deeply fulfilling. Carroll reminds us that the journey of exploration is just as important as the destination. Whether we are peering into the depths of space or contemplating the intricacies of the human mind, we are part of a grand adventure, one that is as much about the joy of discovery as it is about the answers we seek. The final picture. The big picture is not a single truth but a mosaic of insights and perspectives. It encompasses the fundamental principles of physics, the emergent complexities of life, and the subjective experiences that define our humanity. By seeing the world through this lens, we can navigate life's challenges with clarity, purpose, and wonder. In the end, Carroll's message is clear: the universe is what we make of it, and the meaning we find in it is ours to create. Let us strive to live with curiosity, compassion, and courage, embracing the extraordinary gift of being part of the big picture.